couple of examples here with power and specific heat. So a marketing ploy they often do is they talk about tankless water heaters. One of the ideas is you have a water tank here, you have a water heater, you heat the hot water, it's ready for you, so you turn on the faucet and hot water comes out. But they argue that this is inefficient because you're heating water and just storing hot water. Why not just heat the water when you need it? And so you have a tankless water heater. So that means that what happens is the pipe comes in here and circles through the water heater while you're applying heat to it, then the pipe comes out. Okay, and so water comes in at one temperature, comes out another temperature, and you only heat it when you need it. And so the idea is this is more efficient because you're not storing here, because if your water heater is not well insulated, you're leaking heat out. And so, yeah, it is more efficient. But the question is, how much power does it take to do this? Because we got to heat it on demand. And so we know power is the rate of change of energy, right? So power is the rate of change of energy. Well, for mechanical energy, that'd be the rate of change of work. But for thermal energy, that's the rate of change of heating. Remember, heat is the change in mechanical energy, or heat is the change in thermal energy. And so what we need to do is find the amount of heat. So let's say we have a pipe here, goes into our tankless water heater and comes out. We want to heat it. Okay. And so water is going in, and let's say we want water to be coming at 0.25 liters per second. So that's how much water we want coming out here to utilize. Because if we get too little water coming out, then that's kind of like annoying. And so let's say that the temperature going in is 10 degrees. So that's the initial temperature. Let's say the final temperature coming out is going to be 35 degrees. So we have cold water going in, we have hot water coming out. Okay, so the heat is going to be MC delta T. Now, the power is dQ dt. So we take a derivative, C doesn't change in temperature in there, so it's the dm dt. Okay, so we need to know what is dm dt. Well, I have the volume up here. Now, we know that 1 liter has a mass of 1 kilogram. So 0.25 liters is going to have a mass of 0.25 kilograms. So that means that dm dt is going to be 0.25 kilograms per second. So the only thing we need to know left is the specific heat of water. Specific heat of water is 4186 joule per kilogram Celsius degree. So the power for this little water heater is going to be dm dt times C delta T. So that's going to be 0.25 kilograms per second times 4186 joule per kilogram Celsius degree times the difference in temperature between 10 and 35 was 25 degrees Celsius. So the power comes out to be 26,200 watts, or 26.2 kilowatts. Okay, now that's actually a problem, because that's a huge amount of power right there. That actually is, in many cases, more power utilization than a lot of air conditioners. And so that means that your on-demand water heater is going to be ferocious. So what do you do? In fact, that's so much power right there that's unrealistic current for a residential home without special wiring right there. So what do? Your solution is you don't change it by as much temperature, so you don't come out with as hot of water coming out. Well, for a lot of people, that's not a very happy solution right there. The other solution is that you don't have as much water coming out per second. And so that's a more realistic solution, except then people kind of, get this thing and they realize that water's coming out far less quickly than a regular opening of a tap. And then they get unhappy with it. And so you end up with a lot of people that get one of these tankless water heaters and then somewhat regret the decision. Okay. So that's one example of power and heat. Let's do another example of power and heat. Let's consider a farmer, and they've got a barn, and it's a cold day. It's going to get below freezing at night, and you've got things in the barn you don't want to get below freezing. So one way of doing it is put a heater in the barn to keep the barn from freezing. Now you can do that, but then you got to pay electricity. Okay, so another solution is take a couple of very large barrels, paint them black, and set them in the sun so the sun heats them up. And then you roll the barrels into the barn. Now, as the temperature falls, the barrels release heat into the barn. When it starts to freeze, it will not go below freezing until the barrels release enough heat for them to freeze, because they keep releasing the heat. So if you don't care if the barn's cold but not freezing, then this way it will keep the barn from getting below freezing. It'll get really cold and get down to freezing, but not below freezing. So the question is, how much power do you save? So let's assume that you have 750 kilograms worth of water. That would be 2 large barrels of water right here. And let's say when the sun heats the barrels of water, then they get up to 15 degrees Celsius. That's still pretty cool, okay? But now, as you drag them into the barn here, then let's say that you want to figure out, how much heat is released. Well, Q MC delta T, this is the heat released as these barrels cool down to the freezing point of water, plus ML sub F. That's the amount of heat released when they freeze. So all we need to know is we already have the mass of the water. We need to know specific heat of water. That's 4186 joule per kilogram Celsius degree. We need to know the latent heat of fusion of water. So latent heat of fusion of water is 3.33 times 10 to the 5th joule per kilogram. And so we plug all that in. Q equals M times C delta T plus L sub F. Okay, so that'll be 750 kilograms times 4186 joule per kilogram Celsius degree. Freezing point of water is 0 degrees. So the change in temperature was 15 degrees Celsius, and the latent heat of fusion, 3.33 times 10 to the 5th joule per kilogram. And so the heat released turns out to be a pretty large 2.97 times 10 to the 8th joules. Now, let's say the farmer is doing this in the wintertime, so that means at night it's about 14 hours of nighttime. And so that means it's releasing this amount of heat over 14 hours. Well, 14 hours turns out to be 50,400 seconds. So the average power would be the Q over T. So that would be 2.97 times 10 to the 8th joules divided by 50,400 seconds. So the average power is 5.9 kilowatts. Okay, so imagine 5.9 kilowatts, okay, times 14 hours times maybe 10 cents per kilowatt hour, and then for an entire month of like 31 days. And so that turns out to be about $256 that the farmer saves in electric costs by rolling the barrels in and out of the barn. So that's a very interesting sort of calculation right there, and that's why this is sometimes done if you don't really want to be comfortable in the barn, just not freezing.